Hello, everybody. My name is Vladimir. I'm a senior machine learning engineer at DeepSense. And today I wanted to talk about the medical AI as a domain, but from a perspective of an engineer without any special medical education or similar deep dive into the hard science of the thing, just something you may encounter as a regular developer. In particular, not going to be talking about any fancy new technology or a model today, but instead I wanted to give you a quick overview into the domain itself, where the data come from, and most importantly, what are the pitfalls and other unexpected problems you may encounter working with such a domain. And maybe to give you a few spoilers. By the end of this presentation, you'll find out such wondrous things as why your teeth shine under X-ray, why the insurance type you have correlates with your military rank, even if you don't have one, and finally, which body part that is. It's not so obvious. All right. So the first question is, what even is medical AI? The term has gained some decent popularity in the last few years. Perhaps the most well-known instance is the last year's Nobel Prize that has been awarded to, I believe it was Google's DeepMind project that was about decoding and unfolding protein structures. So that's one thing. Other things you might have seen are probably different kinds of diagnostic models that are able to, for example, detect cancer quicker than any human doctor, or detect any other illness in the same fashion. And in general, the definition of medical AI is that it's any machine learning applied to support medicine or healthcare or related tasks. But in my opinion, that's not a very useful definition. And instead, for the sake of this presentation, I wanted to split it into two things. So the first one would be what I call the pharmaceutical machine learning. That's going to include all the hard science, for example, the DeepMind project that I mentioned in a moment. But also clinical evaluations, trials, and all the other things that you probably do need to have medical education for. This part I will not be covering in this presentation because, frankly, I'm not an expert in it in any way. What I'll be covering is the clinical machine learning. And basically, that's everything that faces either the patient or the doctor in a direct way. So that would be the diagnostic models, the imaging utilities, all the data flows, workflows, and other kinds of bookkeeping. And that's something you probably going to encounter if you ever work with a medical AI. So to start, even though in many machine learning domains, it's not critically important to understand where the data comes from, in case of the medical, it is very useful to see the bigger picture, just to understand where the particular problems you may encounter in practice originate from. Right, and when we think of acquiring medical data, what most people think probably is that you come to a clinic, say a doctor, they perform some examinations, take some recordings, maybe do an X-ray or something, drop the report, give you a prescription or something, and that's the end of the story. And while in some cases that is the case, oftentimes, especially now, the system is a bit more convoluted. For instance, clinics sometimes don't really have that much stuff to look at both the patients themselves and also the data acquired, analyze it, describe it. So instead, the clinic just acquires the data and then utilizes the service of third-party analysis centers or laboratories that gather information from multiple such clinics. They have a dedicated team of, say, radiologists or other kinds of doctors. They are looking at your raw data, draft reports, send it back to your doctor, and then they give you a prescription or perhaps a follow-up, in which case you'll go with this cycle a couple more times probably. And during this whole process, we do acquire a tremendous amount of data. So everything from information about the patient, even including some sometimes questionable fields like ID numbers, or in case of the US market, the social security number, which is very much private information. But also the data itself, so the radiological scans, your measurements, linkage to all the past examinations, possible follow-ups, and of course, a fair bit of technical information. For example, which device was used to scan you, with which settings, at what time, who interpreted the results, and so on. And at this point, everything looks kind of great. Machine learning engineers and data scientists do love data. That's our bread and butter. Perhaps the only thing missing at this stage is some sort of a standard to keep everything in place. Because, well, imagine if every single clinic were to come up with their own format of data to store all of that. That would be rather a nightmare. And luckily, we do have a standard. It's called DICOM. It's developed back in mid-80s, I believe. And the main thing about that is that it standardizes a lot of metadata and data itself within itself. So every single bit of information has a dedicated place in the format. Machines know where to write it. We know where to read it. And most crucially, it's the de facto lingua franca of radiology and all the related fields. For example, I'm not aware of a single modern device that doesn't support DICOM format. So we use it all over the place. The format is rather convoluted, I would say, but it does its job very nicely. So it organizes everything into a neat hierarchy of series to scans to studies up to the patient level. And once again, it holds all the metadata you probably may ever need. All right, so that does look a paradise at this point. But as always, we start meeting the reality where everything is not so perfect. So the main problem with any standard or data protocol is that if it's trying to standardize everything, well, it's never truly possible. There's always some pieces of information that are not standardized, either because they became significant after the development of the standard, or the developers just didn't think of it. And to paint you the picture, let's take a look at this thing. So to the right, I put a bunch of fields that are coming directly from the DICOM standard. And to the left, we have a few usually clinically significant pieces of information that unfortunately didn't have a dedicated place in the standard, but we still need to record it in one way or another. And what happens in this case is that people become very creative with where they put certain things. So, for example, the pregnancy status fortunately doesn't have a dedicated field. So people usually just write it to breed description, which is, by the way, usually not used for human patients. The DICOM standard is also applicable to veterinarian branch of medicine. So it has a lot of sometimes underused fields. Okay, kind of makes sense. Next up, the mobility limitations, extremely important for radiology. For example, if you have to take an X-ray, well, it usually goes to occupation. And my favorite one, the insurance type, extremely critical, especially for the US market. Well, as you might have guessed, it goes to the military rank, which is understandably underused in day-to-day practice. So what do we have in the end? Basically, two main problems that come with the DICOM standard and metadata specifically. The first one, as I just shown, the very, let's call it creative use of metadata fields, especially when there is no dedicated place for certain information. But also sometimes people just forget that a certain field exists and try to come up with it with a better placement regardless. Another portion to this point is that sometimes instead of trying to invent their own mapping, as I just showed, people just put this information in, let's say, a free text portion of the file, where you would usually find clinical reports, some follow-up notes, and similar things. That's one. The second one is, well, seemingly innocent, that sometimes we just forget to update the values between the patients. May not sound significant because, well, you have the actual data, you can look at it. So it's no problem for both the patient and the doctor. But imagine this case. You have a lot of data, and let's say you want to create a diagnostic model for pneumonia. In that case, what you typically do is take all the data you have and just filter by the metadata that you have, that you only want the chest X-rays for your training purposes. Well, in practice, you'll find yourself surprised that about, let's say, 10 to 20% of your data set is composed of anything but chest. So this illustration, the picture itself is taken from the public sources, but I've seen exactly the same image being advertised as a chest X-ray, which was hilarious and also very problematic for us. So what can we do about it? Unfortunately, not that much, but I do have a few tips. So first of all, never trust the metadata. Never, ever. Ideally, you should be running your own private annotation rounds, just looking at the actual data, for example, the X-ray scans, or let's say the text reports. They usually contain the information. But if that's not possible for any reasons, just try to look everywhere you can, because you never know when certain information will get misplaced or will encounter another creative use of the fields. Right. Next up, you should be treating every clinical site as its own little world. The mappings I showed in a moment, they may be specific to a particular clinic, for example, and the doctors within that clinic agreed that, okay, we map it this way. In another clinic, it can be a totally different way, and unfortunately, you never know how it's structured. It's just something that people agree on. So what you can do to mitigate that is come up with your own standard. That's the next point. And just map everything to that standard of yours from whatever data you receive. And of course, you have to expect the domain drifts, because once you include new data into your lake, chances are it will be structured differently, it will be annotated differently, so you have to be prepared for that. Right. That was about the metadata, but that's probably not the most I don't want to say not the most important thing, but not the most interesting one. What we usually look at is either text or image data. And let's start with the text. Right, so the first problems arise when you realize that text isn't quite text, actually, at least in many cases. So imagine if you are a doctor and you receive, let's say, 100 of X-rays a day, and you have to describe every single one in great detail, and of course in writing. It would be rather difficult to type it out all manually, and people are usually not huge fans of that. So instead, what many doctors use, and sometimes the whole clinics, are these little microphones that perform speech-to-text detection and basically transcribe whatever the doctor is saying. The problem is that technology is also never perfect. So according to some studies, you get about 7.5–8% of error rate per 100 words transcribed. And even after a physician or other doctor review what has been transcribed, we still get about 1 in 300 words being incorrect. And again, that doesn't sound too bad until you see the actual types of mistakes the software makes. And they range from rather funny ones, like has not been seen by a cardiologist, becomes assaulted by a cardiologist. Well, everybody understands that it's just a mistranscribed piece of sentence. Sometimes the medicine names or disease names get mistranscribed. That's also usually fine, unless you're trying to search for something. But sometimes even very dangerous mistakes happen. For example, 80 units of insulin being interpreted as 80 units of insulin. And well, one of these will probably kill you, so do be careful. But transcription is not the only problem here, of course. For example, abbreviations, they are obviously also used to cut the time typing out the same thing again and again. And they're generally acceptable. So people rarely invent whole new abbreviations by themselves. But the problem still is that a single abbreviation can mean up to, say, a dozen things at a time. And while it's usually more or less understandable from the context of the whole report, I have personally witnessed two clinicians fighting over the interpretation of a particular term in a third-party report. So even they not always can understand what's happening. Right. And my favorite one when it comes to text, hedging. Hedging is all over the place, and you have to be be mentally prepared for that. Well, it happens is mostly understandable because depending on the jurisdiction, a doctor can be found liable if they misdiagnose something or something goes wrong after their diagnosis. So they usually play it safe and include a lot of uncertainties, like it's suggestive, may also, cannot exclude. There is some mild evidence of that. And for us people, it's usually fine. Although for larger models like LLMs, they do trip on these things. I don't know why, but that's what happens. And my favorite part is when the doctors are trying to hide the uncertainty behind very, very complicated and complex structures. One of my favorite examples is something like this. No evidence was found to rule out absence of malignancy. That's, if I count correctly, it's a triple negation. And the question remains, so is there malignancy? Sometimes it can be very tricky to dig through. Right. So what can be done? My first advice is to don't forget the roots of machine learning, even when it comes to natural language processing. And especially in medicine, smaller but more specialized models such as BERT, Roberta, or any of the dozen of variations of that, they work extremely well. And what's nice about them is that you can always easily retrain or fine-tune these models to achieve a specific goal. And also to that point, don't try to solve the whole range of problems at once. A huge model, for example. Go step by step. For example, first to solve the uncertainties, then the negations, then mistranscriptions, and so on. Second point, very similar to the first one. Heuristics are, well, they're all over the place in medicine. Especially common are regular expressions, and I've seen code bases being composed of, 80% of regular expressions. And they help tremendously trying to resolve abbreviations or similar kinds of things. And finally, it's best that you have somebody with actual clinical background experience in your team. Not necessarily as an engineer, but just a consultant, because the domain knowledge is critical, and especially when it comes to mistranscriptions and abbreviations. Sometimes you cannot just figure it out by yourself just looking at the data. You need somebody who knows how this kitchen works. Right. Next up, computer vision. It will be a rather shorter section of the presentation, but I would say important nonetheless. And in general, computer vision is way less problematic because that's just the data acquired, almost as raw as it gets. But even here, we have certain problems. First thing you'll notice is that firstly, you have a lot of high-dimensional data. So, for example, X-ray or ultrasound, rather simple because they're just 2D grayscale images most of the time. But when it comes to CT, MRI, it gets 3D. And in rather rare cases, but sometimes you can even encounter 4-dimensional sequences. Most of the time, it's 3D volumes over time for certain kinds of MRI, most commonly. And again, that's usually fine. But what you'll notice is that computational expense explodes very drastically with dimensionality. Even if you compare, say, a 2D convolutional network to a 3D one, the smallest 3D one will probably be much slower than the 2D one. And when it comes to storage, just expect that a single MRI scan can be a few gigabytes. And if you're unlucky and encounter a rather rare but whole body scan, it can easily be just 20 gigabytes or more. It's usually not bounded. Okay, the next thing, artifacts. There are all kinds of them, sometimes ranging from completely broken data, as you can see on the picture A here. Sometimes it's recoverable, for example, when the patient moves and it's just a bit blurry. But my favorite one is something called bloom. You can see it on the bottom right picture. It's very common on X-rays and CTs. It basically happens because some patients have metal parts in their body, most commonly in teeth, as an implants. And these implants, they scatter the rays of X-ray. So you see these little nice flowers on your scans. Right. So how do we mitigate it? First thing, again, do not ever use the metadata as a single source of truth. Once again, it's better to run your own rounds of annotation, again, if possible. If not, a very nice technique that worked for us many, many times is weak supervision, or semi-weak supervision, rather. When you take a small portion of the data, annotate it manually, and just use it as a baseline to bootstrap the model on more and more data. And one more technical tip I have is to take a look at something called ISL loss. It stands for asymmetric loss for multi-label classification. Help us tremendously, especially when it comes to hierarchies when you have overlapping layers or very similar concepts. And the second thing is something called SEM, but not the segment anything model, but the slightly older algorithm called sharpness-aware modeling, which basically helps your model stay on the smoother side of the gradient without jumping all over the place, and makes it way more predictable and interpretable. Okay. Second thing, as I mentioned, the amount of data you receive is huge. So one thing you can do is to try and minimize it as much as possible. For example, if you don't really care about fine little details, you can always either compress the images, or when it comes to, for example, 3D data like MRI, you can always try to merge the slices or try different 2.5D approaches. That almost always helps. If you're doing something more detail-oriented, like, for example, segmentation, the standard approach is to not look at the whole volume at once, but just take a sliding window, chunk the volume, process it separately, and just merge everything in the end. And last tip here is not to be afraid of harsh augmentations, especially when you keep in mind the range of possible artifacts you can see in actual practice. The more augmentations, usually the better. All right, and the final part is not exclusive to the computer vision per se, but more of general machine learning, is to always use the right metrics. For example, if you're doing just plain old classification, the metric correlation coefficients are usually slightly better than the F1 score because they're symmetric and don't depend on your choice of the positive and negative cases. You shouldn't fear creating your own metrics because sometimes you have to do something rather unorthodox, and the goal is complicated and plainly cannot be explained in the standard metrics. And of course, you have to balance your metrics for the specific use case. For example, if you're doing anonymization, the cost of letting private information through is much higher than redacting something that is not private. So you want to prioritize recall over precision. And this is applicable to all cases of machine learning in medicine. And finally, just a general tip, always visualize your data, because at first it may not be very understandable to an untrained eye, but after a couple of weeks, you'll get the gist of it and probably will be able to interpret the data as well as the radiologist to some extent. All right. Why is MCC better than F1? Because it's symmetric, as I said. F1 can be biased towards the selection of the positive and negative cases. MCC is resistant against it. All right. So that was mostly it from my side when it comes to tips, tricks, and problems that you may encounter. Let's just do a quick recap of what I mentioned so far. So the first and most important point, never trust the metadata. If possible, annotate manually. You should always keep somebody with actual clinical experience around. Just remember that the text and image artifacts are very common in practice, and you'll see it all over the place. Build adapters for every site, again, because in some places they use one convention, in other ones they use something else. And again, if possible, try to trim the fat of your data as much as possible. It will save you a lot of time and nerve trying to dig through all of that instead of just looking at the most important things. And the last advice, fear or not, the medical AI. It may sound intimidating, but in practice, you'll learn it very fast and just get used to it. Right. So thank you for your time. It was a great time presenting it. And I would be glad to answer your questions.